Okay, perfect. Now, for the next part of the session, let's click on this folder called Bracket Workshops. I will make it a little bit bigger so that everyone can see. And we have that up here. And then immersion days. And in there, we have quantum tasks. You click onto quantum tasks. There is this notebook called quantum tasks. Okay, we'll be working through this notebook. Getting started with Amazon Braket. Is everyone able to get to this point? Just a couple of yeses or no's will be very helpful. Okay, all right. In that case, let's go ahead. So I encourage you to go through this notebook and read a little bit more in detail. Basically, what in this notebook we are going to do is we're going to design and build a quantum circuit, which we just learned about, Bell circuit. Then instantiate a device object. It will be a local simulator for this demonstration up here, but you can run it on, and we will run it on on-demand simulator. Unfortunately, the QPUs are not available at this very moment, but when they become available, you can run these on QPUs as well later. I'll show you how. And then we'll be looking at how to create this, how to create a quantum task and submit it to run on a simulator and a QPU device. And then we'll see how to retrieve the result. Okay. So let's build the very first simple quantum circuit. So we have two qubits, one Hadamard and one CNOT gate. So for that, we just import this object circuit from bracket.circuits. So you start with circuit parenthesis. So just this part, circuit parenthesis, it just creates an empty quantum circuit object, right? There's nothing in it so far. Then when we add H0, it adds one qubit and in state 0 and applies Hadamard gate to it, like up until this point. Then you apply C0 with control on 0 and target on 1. Then it adds a second qubit and builds up this circuit. Okay. And when I run this and print this circuit, it looks something like this. Like qubit 0, qubit 1, we have Hadamard, C0, and that's what the circuit is. Okay. Is there any default definition of qubit? What do you mean? Okay. If you mean by default state of qubit, yeah. So when you instantiate a qubit is instantiated in state 0. Yeah. How much hardware resources can we expect a simulator to use? So a simulator, if you're running on a local laptop, basically on a standard laptop, you should be able to do run 15 to 20 qubit simulation. But please keep in mind that for every qubit you add, the memory requirement doubles. So from 20 to 21, if you are upgrading a qubit, then you will need twice as much memory as you would need for the 20 qubit. What is T displayed in timer? Is that time T as in a label for time, like at 0th level or first and so on. So this is like first level, second level of quantum. The T is depth, you can see. T is depth of the quantum depth of gates. Okay. All right. Now, if somebody asks like what kind of gates there are in quantum, like quantum, okay, what is quantum depth? Like depth of the circuit, basically how many levels of quantum circuit you're applying. Like a single layer will be just Hadamard, second layer will be Hadamard and C0. So how many independent, like how many successive application of gates there are? Like if you are like 100 cycle of gates like applied, that would be quantum depth. Not quantum depth, like that's the wrong term. Depth of the quantum circuit. Okay. If you run this, like for instance, it shows all the different gates of gate sets, like CC0, C0, phase shift, control V, control Y, control Z, all sorts of gates are possible in quantum mechanics, right? For the experts in the audience, if you want to, instead of applying quantum gates, if you want to add a unitary to your quantum circuit, this is how you can do it. Like you can define your unitary in terms of a matrix and just say my circuit.unitary, and it will run it for you. But please keep in mind that unitary you can only simulate using simulator. Just by writing the unitary, it won't run on a quantum hardware, because to run on a quantum hardware, you would need to provide the compilation of this circuit in terms of gates. So now we have a Bell circuit that we want to simulate and execute the circuit on local simulator, right? So local simulator is, as I mentioned, it's a simulator that comes by default with the Braket SDK. You don't need to install this separately. All you need to do is just say device is equals local simulator, and that does it for you up here. And then life is simple. All you need to do is device dot run and give the name of the circuit, that is Bell, and shorts. Okay, now comes interesting point, shorts. So remember I told you that when you run a quantum circuit, you try to build statistics, right? You run the quantum circuit a bunch of times to build statistics. Those are shorts. So a single run of a quantum circuit is called short. So when you submit a circuit to a quantum hardware, you say that, okay, I want to submit, run this circuit n number of times to build statistics, and that n is the number of shots. Okay, so that's what you're doing. You are running the same circuit 1,000 number of times to build statistics. So when you do this, a task is created, right, and submitted for run. Okay, so when you do this, if you run the cell, your task is created and task.state. So the state of a task is already completed, because on a local simulator, since you don't need to go in the queue or don't need to wait for resources to be available, as soon as you submit the task, it is completed. Now the task is completed. We want to see the results, right? And if you click, if you run this cell, task.result, the result has like a lot of information, right? I mean, it has some metadata about your job, about the quantum task, how many shots you ran, what was the device, and so on and so forth. And if you're interesting, if you see the measurement part of this result, it says array of outputs. So array of 1, 1, 1, 1, 1, 1, 0, 0, 1, 1. So it's showing that all the 1,000 outputs that you obtained. Okay, so that's that. And at the end, you also have measurement counts. Like out of those 1,000 outcomes, how many were 1, 1, and how many were 0, 0? Okay. So again, let me ask you, why do you think you have only 1, 1, and 0, 0? Why don't we have 1, 0, or 1, 1? Or like 1, 0, and 0, 1? Any guesses? Yes, because C naught gate, and because it's a Bell circuit, right? In the Bell circuit, the output can only be 0, 0, or 1, 1, right? That's why you have only either 0, 0, or 1, 1. Okay. So now we can just from results, we can get the measurement counts and plot them basically. And if you plot them, this is what the bar graph looks like. For 1, 1, and 0, 0, they're approximately close to each other, like approximately half and half, right? They are not exactly half and half, because it's statistics, right? In statistics, you never get like 50% now, like exact answer. It's always there is some difference, and that difference is because we are sampling. We are doing the reverse engineering. We are building the probability by looking at the outcome, So there is always going to be some uncertainty. So that's what this is going to be. So we ran this on a simulator, right? But now just imagine a scenario that if we ran this on a QPU on a real quantum hardware, do you expect any differences in the answer? And if you do, why? Let's think about it. Like, okay, noise. So yeah, noise will be there in the quantum hardware, error noise, that's right. But what is going to be, how is noise or error going to affect the answer, the final distribution or the final outcome of this circuit? Yes, the correct answer is there will be some contribution from like 1 and 1, 0 outcomes as well, right? Because of the noise, the final state is not going to be exactly correct. There's going to be some contribution from like 0, 1 and 1, 0 as well. Okay, and depending on the noise, those contribution could be high or low. Okay, so that's what I was trying to get to. Now you can build a more complex circuits, right? I mean, now world is your oyster. You can just, put add any number of quantum gates and build a circuit. So let's go to another level. Instead of just looking at 2 qubit, we can look at multiple qubits. Uh, right? And here I'm showing you like a circuit called GHZ circuit. And GHZ circuit is basically like generalization of Bell circuit to a higher number of qubits. So for example, for 5 qubits, we have one Hadamard and then 1, 2, 3, 4, 4 CNOT gates, right? And the idea is that at the output, you'll get either 5 zeros or 5 ones, similar to you're getting for two qubits. Where do these noise occur? In the qubits, in the circuit, or both? So the noise occur at many levels. So the noise can be in the qubit itself. The noise could be due to like the electromagnetic pulses that we apply to apply quantum gates. And the noise could be due to some thermal noise. So all different kind of noises are possible. Uh, what you can do is we can model these noises in terms of certain gates, right? You can represent these some of these noise uh, in terms of basic elements, such as uh, there are some noise which will cause a bit flip error, right, with some probability. So you could add a quantum object that introduces a bit flip, a random bit flip. So that is kind of a noise as well. So at a hardware level, there are many sources of noise, but you can model those noise on a logical level by introducing what is called Krauss operators and so on. And you can read more about it on Braket documentation in the noise section. Okay. A basic question for the simple Bell circuit. The Hadamard gate creates a superposition 0 and 1. How do we then end up with 0, 0 and not a hybrid output? So we are ending up in a hybrid output. This hybrid output is actually, so Hadamard gate, the hybrid output was 0 plus 1 divided by square root 2. And in this case, the hybrid output is 0, 0 plus 1, 1 divided by square root 2. So it is instead of calling hybrid output, call a superposition output, right? And uh, in this Bell circuit, if you run this, let me show you something. Instead of running 1,000 number of times, let's run this. Uh, so, okay, so we are running this 1,000 number of times. Now let's just run it once. Okay. What is the output you get? It is 1, 1 this time. You run again, it's 1, 1, 1, 1, 1, 1. Oh my, 0, 0, right? 0, 0 is 1, 1, 0, 0. So in this sense, it is still a like a mixed output, right? Sometimes it's giving 0, 0. The other times it's giving 1, 1. And just like in case of Hadamard, Hadamard was applicable to a single qubit, and this Hadamard plus C naught is being applied to 2 qubits. So Hadamard was giving a superposition outcome in a single qubit, and this one is giving superposition outcome into 2 qubits. Okay. Now, if you want to do this, the same thing to n qubits, this is how you can do it, like GSZ circuit, right? And I leave this as an exercise to run this on a local simulator for you. And now let's try to submit this on on-demand simulator. Okay. So far you were using local simulator, and to run an on-demand simulator, you will need to import this object called AWS device. And you can get devices, different kind of simulators available. And to to use any of this simulator state vector 1, for example, all you need to do is like call device equals to, instead of local simulator, you call it AWS device and give this ARN, ARN or ARN. You can get the ARN either by like typing get devices, or you can go to Braket console, go to devices, state vector 1, and then there is a device ARN here. ARN stands for Amazon resource name, and you can copy that and you can just paste it here as a string. So when you run this, device is set to state vector 1. Okay. Now later, if you want to run the same circuit with a different device, all you would need to do is just copy the ARN of that device and change just one line of the code here, and keep the rest of the code exactly the same, and it will run on a different device, right? So that's the one of the advantages of working with the like Amazon Braket here, is that you need to change one line, just one line of the piece of code, to change the device on which you would be running. There is another way you can set your device, and that is by either by saying name, like devices.amazon.sv1. It is the same thing. It happens the same thing actually. Okay. Now we have set our device to be state vector 1 simulator. And now let's run a 20 qubit, a GHZ circuit, right? And once again, GHZ circuit is like a bell circuit, but for 20 qubits, right? Okay, so now if I run this, initially the task is created. When I run it again, task is completed. Again, like it's such a short period of time that the job has already completed. Now, before I run this, okay, I want to ask you, what output do you expect for 20 qubit GHZ circuit running on state vector simulator? Feel free to unmute yourself and answer. More uniform, what does that mean? More uniform. I didn't quite understand the answer there. Okay, so before I go, like, how many zeros and ones do you expect in one output? It's a 20 qubit circuit. 20. Okay, so you will get, in each sample, there will be 20 qubits. And how do you expect the outcomes to be? Do you expect them to be like all zeros, all ones, a mixture of them, or some of them ones, some of them zeros, or how? Yeah, so the answer is going to be, it's either all zeros or all ones with 50% probability, right? Because, I mean, I did not tell you what the state of the qubit GSA circuit is, but like I briefly told you that it's like a bell circuit. but for larger number of qubits where either outputs are all zeros or all ones. Okay, so now 20 qubit, the circuit we run it, and this is what the outcome is going to be, right? Almost half of the times it's all ones or all zeros. Okay, then now the question is like what happens if we add noise to it, or like run it on a real QPU, real quantum hardware? The answer would be that we would have contribution from other bit strings as well, like 100111011 or something like that, right? Not all of them. In addition to these two outcomes, depending on the noise of circuits or noise in the circuit, you will have other outcomes as well. So that's where the state vector will. Right now, every task has like a unique ID. So like, let's say you submit a task, a quantum task that goes in the queue, then you don't have to wait around for you to be there for the results to be come out. Or you can let the task be in the queue, and when it's completed, you can use the task ARN or task ID to recover the results of that task, right? So for example, let's say you want to run your circuit on a QPU. So I advise you not to do that right now because this device is currently offline. Well, not offline, it's not available. It will be available in 8 hours. Yeah, Oxford Quantum Circuit is going to be available in 7 hours approximately. Then you can submit this task to run. Okay, so like for example, if I do this and I submit this to Lucy, right? Lucy is here, and copy device ARN, and I advise you not to do this. I'm just doing it to show you how it works. And I do this, I have submitted, and when I execute this, it's saying that the task is created, right? And since the device is currently not back online, the task will be created until, it will be created. Okay, so if you go to your quantum tasks, you should be able to see all your quantum tasks that you have run or submitted. So we submitted a state vector 1 job that has been completed, and you can see. But I cannot see the job that has been created, this Lucy. Like this, I submitted a job to run on QPU by Oxford Quantum Circuit, which is on European West region. It has been created, but I don't see that job anywhere in this quantum list of quantum tasks. Why do you think that might be? I mean, I just want you to like take a guess. I mean, I'm not sure if you'll be able to guess the answer, but just as an exercise. There's a question: is the noise in the simulator here equivalent to that in the quantum hardware? There's no noise in the simulator here that we are using. So I'm not sure if what you mean by the noise here. If you're referring to the differences between like 1 and 0 0 not being exactly 50%, so that is not due to noise. That is due to the basic nature of sampling statistics, that they are not exactly 50%. If you increase the number of samples to infinity, like if you keep increasing the number of samples, then you would see them becoming more and more 50-50, and they will approach to 50-50. I mean, that is like central limit theorem, right? Okay, so let me tell you the answer why you don't see the quantum task created up here. Because you see, this device, Lucy, is in a region called EU West, right? EU is European, West region 2. And we are currently in North Virginia region, which is US East 2. So to see the status of that quantum task, you would need to go to US2 and click on US2. Okay, and you go to quantum task, you will see that there is a job or there is a task created that is waiting. If you click on there, you will see that we have created this task. There is a 13, queue position is 13, like there are 12 quantum tasks ahead of this task. We submitted with 100 shots, and it's been created. So it's waiting in the queue right now. But we don't have to like keep waiting for it to, for us to get the result. Like for example, right now, if you want to see the queue depth, just say that there is a queue position 13, and like there is a 14 depth of the queue. So you can come back later. All you would need to do is to recover or like get the result of a quantum task. Like just provide the ARN of the quantum task. Like for example, this is the quantum task. You can copy the ARN and paste it here and run it. So again, like since the task is still created, it hasn't completed running, it is showing that the status of the constructed task is created. And then if you run this cell, it's saying that, sorry, your task is still being processed. So since it's not completed, we don't have the results yet. That's why we can't see the outcome of this result in terms of 50-50 or like whatever results outcome from QPU would be. So, but yeah, the idea is that this is how you can obtain the results from a QPU once you submit it to a QPU, okay, and recover the results later. Unfortunately, at this moment, there are no QPUs available that we can experiment with. But yeah, in the next 72 hours, when you have time, you can try to run these jobs or tasks on Lucy Oxford quantum circuit device. Okay. Are there any questions that I can answer before I ask you a question?
Please feel free to unmute and ask so we know you get everything. Oh, there's a question from Nelson. In general, how many shots can we expect is sufficient?
I mean, that totally depends on your algorithm and what you would need, right? Um, uh, I mean, in general, like number of shots is like depends on the algorithm that you want to use. But usually like a couple of thousand shots, it's a standard. Okay, let me ask you a question here. So as we saw, like we ran a 2-qubit Bell circuit and 20-qubit GSC circuit on a state vector device. And here on Lucy, Oxford quantum circuit, we are submitting 8-qubit GSC circuit. What do you think will happen if instead of 8, I put number 20 here? I mean, of course, you will get this 20 circuit, right? What do you think will happen if I submit that circuit to run on this device? Let's say if I submit that, it's giving an error. Exactly. It will not work because Lucy can only support 8 qubits, and that's what this error is going. So whenever you submit a quantum task to a simulator or a quantum circuit or a quantum device, you need to be mindful of the number of qubits that there are and the resources that it can support. So that's what the catch was here. Okay. All right. So in terms of material, this is what I had planned for today's talk, and I was hoping, I mean, you were a great audience. I mean, you asked many questions, and for the remaining amount of time, I will open the floor for questions before going to the presentation at the end. Are there any questions?
Feel free to put your question in the chat or to unmute yourselves and ask Brajesh directly. Might take a moment, Brajesh, to formulate a
Sure.
question.
Yeah, sure. In the meantime, I'm pasting a link up here in the chat. So this is linked to a survey, and this survey basically is about your feedback on the session that we did today. Be brutally honest and tell me what you didn't like, what you liked about this talk today, and this helps us really, improve our sessions and for future iterations. So uh, I would appreciate if you could it takes 2 minutes to go through this survey and complete it. Albert, would you be able to circulate this survey link to
Sure.
to the participants so that they can take a look later?
Yeah, sure. I'll
Simulator
repost
works
the
on
link.
Yeah, thank you. So simulator works on local laptop. Yeah, so on a local laptop, only the local simulator will work. The first example that we saw, local simulator. To access the SP1 and DM1 and TN1 managed simulators, you would need access to AWS Cloud. You can submit the quantum task using your local laptop, but you will need AWS account to run on SP1, TN1, or DM1. Is Amazon AWS working in any in-house quantum hardware? If so, which architecture, please? Uh, I'm not. I'm not entirely sure if I can share the information about architecture, but yeah, the answer is that Amazon is working on a in-house quantum computing hardware. For any more detail, uh, stay tuned.
Any further questions?
I just have a more simple one, alluding to a question I asked earlier. So the reason why we're sampling is because when you're measuring, like from a quantum circuit, is it because the wave function collapses and you just get one result? That's why you have to do multiple sampling to model, because you cannot measure the wave function itself. Is that why
Right.
the sampling is done?
Yes, that's right. Exactly.
Okay, now that makes sense. Thank you.
Thank you. I mean, you can think of it in like a classical sampling problem. Like in a classical sampling, if a distribution is given to you, or if the distribution is not given to you, probability distribution function, and if you want to like build that probability distribution function, you will need to sample. Like you collect samples and then see like what the probability of various events is going to be. Here, the difference is that probability distribution function is coming from a quantum operation. And at the end, you are getting some like probabilities out of it. On the same lines, can we recover wave function? Very good question. So to recover wave function, you would need only the measurement of probability is not enough. You would need the phase information as well. Okay, and that you could do by like phase estimation and things like that. Any tutorials on that? You can maybe look at state preparation and measurement. State preparation and measurement. Um, I'll have to look at resources uh, for that. But you can look at like online, there are many resources, preparation, measuring the wave function. Yeah, quantum measurements, like for example, you can look at it, how you can do that, or quantum state vectors. Like basically look at any tutorial of measurements in quantum mechanics.